The journey to finding life in the universe heavily depends on the balance of carbon dioxide with other gases in a planet's atmosphere, along with the presence of specific biomarkers that could suggest life's existence. Imagine a scenario where life thrives on heme planets, worlds that are 2 to 4 times the size of Earth and enveloped by a single vast ocean. These so-called heme worlds, classified as subneptunian planets, have sparked significant interest among scientists. Such water worlds came into the spotlight when the James Webb Space Telescope detected substantial amounts of water and a hydrogen-rich atmosphere on exoplanet K2-18b, indicating the possible presence of an enormous ocean and potentially life. K2-18b, an exoplanet 6 to 8 times Earth's mass, orbits the cool red dwarf star K2-18 within its habitable zone and is located about 120 light-years from Earth. With a size between Earth and Neptune, the discovery of both methane and carbon dioxide in its atmosphere, along with the absence of ammonia, supports the theory that K2-18b could harbor a water ocean beneath its hydrogen-rich atmosphere. Additionally, the James Webb Telescope identified traces of dimethyl sulfide, DMS, on K2-18b, a molecule produced solely by life forms on Earth, particularly by marine phytoplankton. Further observations by the telescope are expected to confirm this finding, which could provide substantial evidence of biological activity on the planet. Life on K2-18b could range from simple organisms, like plankton, algae, and microbes, to more complex aquatic creatures, such as fish or even marine mammals. The potential for advanced life forms on other planets may far exceed our current understanding. Even in a completely ocean-covered environment, more sophisticated organisms could have adapted to living in such aquatic conditions. Whether K2-18b has landmasses remains unknown, as they are difficult to detect remotely. Adding to the intrigue, the James Webb Telescope can also detect artificial light emissions, such as those from potential cities on distant planets, marking a significant advancement in the search for extraterrestrial life. Interestingly, K2-18b was first discovered not by the James Webb Telescope, but by the Hubble Space Telescope, which initially provided insights into its atmospheric composition. The promising data from Hubble led researchers to re-examine the exoplanet with the new telescope, resulting in groundbreaking discoveries about K2-18b. This research offers a fascinating glimpse into what might be our first detection of signs of life beyond Earth. This discovery is monumental, especially considering that nearly a century of searching within our own solar system has yielded no conclusive evidence of life, although the icy moons orbiting Jupiter and Saturn remain potential candidates. High-end exoplanets like K2-18b could indeed be classified as superworlds and possible cradles for various forms of life. Life on Earth originated in water, with land masses and terrestrial life evolving later. If Earth had remained an entirely aquatic world, intelligent life forms might have evolved solely for marine existence. Traditionally, the search for extraterrestrial life has focused on Earth-like, smaller rocky planets. However, larger heme worlds are now being considered as superworlds within the vast cosmos. Not all scientists share this optimism, though, as it's possible the oceans on these planets may be too hot to support life. In such cases, heme worlds could resemble immense steam baths. However, life's resilience is well documented, even in extreme environments like the hot, toxic geothermal pools of Yellowstone National Park. The study of K2-18b raises the compelling question: could we ever truly confirm whether an exoplanet is inhabited? If intelligent life were discovered, humanity's instinct would likely be to establish contact. However, K2-18b, at approximately 124 light-years from Earth, presents a considerable challenge for our current space travel capabilities. Our space probes, taking years just to reach nearby destinations, face an even more daunting journey to a planet 124 light-years away, or even to one as close as 4 light-years. The Voyager probes launched in the 1970s, for instance, will take thousands of years to reach the nearest star systems. Connecting with extraterrestrial civilizations would require novel approaches. The search for Earth-like planets within nearby star systems, such as Proxima Centauri, inspired Yuri Milner to propose the concept of nanoships. Small probes equipped with cameras that could travel trillions of kilometers in a matter of years, capturing images of planets that might harbor life. If an advanced civilization were found in space, scientists would likely develop entirely new methods for communication. These ambitious goals drive our spirit of exploration and innovation. In a speculative future where warp drive technology might enable faster-than-light travel, visiting worlds like K2-18b could become feasible. However, our current space travel relies on Newtonian physics, with propulsion systems dependent on fuel and thrust. Even if a spacecraft capable of traveling at 10% of the speed of light were built, the journey to K2-18b would still take approximately 1,240 years. A radio signal, traveling at the speed of light, would take 124 years to reach this distant exoplanet, with a reply arriving another 124 years later. In sum, the example of K2-18b highlights the tremendous strides made in the search for extraterrestrial life. The exoplanet, discovered around 120 light-years from Earth, has become a focal point for researchers due to its unique features suggesting possible habitability, and even life. This in-depth exploration delves further into the scientific backdrop of K2-18b, the technological advancements involved in discovering distant universes, and the possibilities it presents for understanding life beyond Earth, drawing us closer to answering one of our most profound questions. Are we alone in the universe? The journey to unveil the mysteries of exoplanets, the potential for life, and the broader implications for our understanding of the cosmos continues to inspire and challenge scientists and experts worldwide. Methods for studying exoplanets. 1. Transit method. The transit method is a primary approach for detecting and studying exoplanets. This technique involves monitoring a star's light curve for periodic dips in brightness, which occur when a planet passes in front of the star from our perspective. The amount of dimming reveals information about the planet's size, while additional observations help determine its orbit and other characteristics. The Kepler Space Telescope was instrumental in discovering thousands of exoplanets using the transit method, identifying numerous planets within the habitable zones of their stars, significantly advancing our understanding of exoplanet demographics. 2. Radial velocity method. The radial velocity method measures a planet's gravitational effect on its host star. As the planet orbits, it causes the star to wobble slightly, affecting the star's light spectrum and creating red or blue shifts. By analyzing these shifts, scientists can infer the planet's mass and orbit. Instruments like the HARP spectrograph, High-Accuracy Radial Velocity Planet Searcher, have been crucial in detecting these slight variations in star velocity, contributing to the discovery of many exoplanets. 3. Direct imaging. Direct imaging captures photographs of exoplanets by blocking out the light from their host stars. This approach is challenging due to the star's brightness compared to the faint light from planets, but it can provide detailed data on a planet's atmosphere and composition. The Very Large Telescope, VLT, operated by the European Southern Observatory, has successfully imaged exoplanets and studied their atmospheres directly. 4. Gravitational microlensing. Gravitational microlensing occurs when a massive object, such as a planet or star, passes in front of a more distant star. The foreground object's gravity bends the background star's light, causing a temporary brightening that telescopes can detect. This method is particularly useful for finding exoplanets far from their host stars. Projects like OGLE, Optical Gravitational Lensing Experiment, and MOA, Microlensing Observations in Astrophysics, have used this technique to discover exoplanets. Broader scientific implications. 1. Astrobiology. Astrobiology is the study of life in the universe, encompassing the origins, evolution, distribution, and future of life on Earth and beyond. Discovering exoplanets with potentially habitable conditions marks a major step forward in this field, offering a framework to understand the potential diversity of life forms and the environments they might inhabit. Studying extremophiles, organisms that thrive in extreme environments on Earth, provides insights into how life might survive in harsh conditions on other planets, such as extreme temperatures, pressures, and radiation levels. 2. Habitability models. Understanding habitability involves modeling the conditions necessary for life to exist, including temperature, atmospheric composition, and the presence of liquid water. Scientists use these models to assess which exoplanets could have environments similar to Earth's. Studying planets within our solar system like Venus and Mars refines habitability models, offering insights into atmospheric dynamics and their effects on surface conditions. For example, Venus's runaway greenhouse effect and Mars's thin atmosphere inform our understanding of planetary climate and habitability. Philosophical and cultural implications. 1. The search for meaning. The search for extraterrestrial life challenges our understanding of humanity's place in the universe. Discovering even microbial life on another planet would have profound implications for our sense of uniqueness and our philosophical views on life and existence. Such a discovery could shift our perspective from seeing Earth as the only known cradle of life to realizing that life might exist elsewhere, altering our worldview. The discovery and study of exoplanets like K2-18b represent a significant leap in our quest to understand the universe and our potential place within it. Situated within the habitable zone of its host star, K2-18, a cool red dwarf, K2-18b has sparked interest because this zone allows for the possibility of liquid water, a key ingredient for life as we know it. Significance of K2-18b. K2-18b's size, which falls between Earth and Neptune, makes it an ideal candidate for studying atmospheric and geological characteristics. This exoplanet offers scientists a unique opportunity to analyze signs of habitability and gather information on the types of environments that may support life. Atmosphere composition. One of the most compelling aspects of K2-18b is its atmospheric composition. Observations from the James Webb Space Telescope, JWST, have revealed a hydrogen-rich atmosphere containing water vapor, which suggests the presence of substantial water content, potentially a vast ocean. The detection of other gases, such as methane and carbon dioxide, strengthens the hypothesis that K2-18b may possess a greenhouse effect, which would help maintain temperatures favorable for liquid water. Methane is particularly noteworthy because, on Earth, it is largely produced by biological processes, hinting at the potential for biological activity on K2-18b. Additionally, the absence of ammonia, a common toxic gas, suggests that the environment might be more hospitable. Technological advancements enabling discovery. The detection and analysis of K2-18b would not have been possible without significant advances in space telescope technology. The JWST, a marvel of modern engineering, has enabled unprecedented detail in studying distant exoplanets. Equipped with powerful infrared capabilities, the JWST can penetrate the dense clouds of gas and dust surrounding exoplanets and their stars. This level of detail allows scientists to investigate the atmospheric composition of exoplanets, revealing critical insights that were previously unattainable. The JWST's capacity to detect molecules like dimethyl sulfide, DMS, is particularly significant. On Earth, DMS is produced almost exclusively by life forms, especially marine phytoplankton, making its detection on K2-18b a potentially strong indicator of biological activity. The search for extraterrestrial life. The search for extraterrestrial life involves various approaches, from examining exoplanet atmospheres to detecting signals from advanced civilizations. Discovering habitable exoplanets like K2-18b is a critical step in this journey. Biomarkers, molecules that suggest the presence of life, play a crucial role in identifying biological activity on distant planets. The presence of gases such as methane and oxygen in specific combinations is considered a strong indicator of life, as these gases on Earth are largely produced by living organisms. The Drake equation and potential civilizations. The Drake equation, a formula used to estimate the number of active extraterrestrial civilizations in the Milky Way, considers factors like star formation rates and the fraction of planets that could support life. Findings from K2-18b and other potentially habitable exoplanets add valuable data to refine our estimates, guiding future searches for extraterrestrial life. Challenges and future prospects. Despite the exciting discoveries, studying exoplanets like K2-18b presents significant challenges. K2-18b is located 120 light-years away from Earth, making it inaccessible with current technology. Traveling such vast distances would require breakthroughs in propulsion, as current spacecraft would take thousands of years to reach even the nearest stars. Emerging concepts such as nanospacecraft, like those being developed under Yuri Milner's Breakthrough Starshot initiative, aim to reduce travel time. These tiny probes, propelled by light sails, could potentially reach distant exoplanets in a fraction of the time it would take traditional spacecraft, capturing detailed images and data. Other hypothetical technologies, like warp drives that would allow faster-than-light travel, offer a glimpse into a potential future, though they remain in the realm of scientific speculation. Broader implications. The discovery of potentially habitable exoplanets like K2-18b has profound implications for our understanding of life in the universe. It raises questions about the potential for life beyond Earth and the conditions necessary to support it. By studying planets like K2-18b, scientists gain insights into the types of environments that could sustain life and the diverse forms life might take. This knowledge can inform our search for life on other planets and guide future missions. Philosophical and cultural impact. The discovery of extraterrestrial life, or even the potential for it, has far-reaching philosophical and cultural implications. It challenges our understanding of our place in the universe and could inspire new perspectives on our own existence. The search for life beyond Earth is not just a scientific endeavor, but also a journey that addresses fundamental questions about humanity's role in the cosmos. Conclusion. The exploration of exoplanets like K2-18b represents an exciting frontier in our quest to understand the universe. As technology continues to advance, our ability to detect and analyze distant worlds will only improve, bringing us closer to answering one of humanity's oldest questions. Are we alone in the universe?